Welcome back to the session on bulk nanostructured materials. In the last session, we have seen what are bulk nanostructured materials, their classification and the production methods of some disordered bulk nanostructured materials. In this session, we will think about certain special properties of bulk nanostructured materials. We have already seen that the bulk nanostructured materials have some interesting properties such as increased yield strength as compared with normal bulk materials. In this session, we will discuss that in detail. But before that, we will try to learn why the normal bulk materials do not show the special properties of bulk nanomaterials. What is wrong with the normal materials? We need to learn the reasons for the mechanical failure of normal bulk materials, or more precisely the failure mechanisms of conventional grain sized materials. Although there are many reasons for the mechanical failure of conventional grain sized materials, we discuss two main reasons, and those reasons are: number one, fracture and brittle to ductile transition. Brittle to ductile transition. There are other failure mechanisms also, but we will restrict our discussion to these two most important failure mechanisms. Let us start with fracture. Fracture occurs due to the existence of cracks in the material. Fracture occurs due to the presence of cracks. Now, what are cracks? A crack is a region of a material where there is no bonding between adjacent atoms of the lattice. A crack is a region of a material where there is no bonding between adjacent atoms of the lattice. Look at the figure. The figure shows such a crack in a two-dimensional rectangular lattice. And what is wrong with crack in a material? When a bulk material is subjected to a tension, the crack in the material interrupts or blocks the flow of stress. As a result, the stress accumulates at the bone which is at the end of the crack, and after some time the stress becomes stronger than the bond strength, and then the bone breaks. Consequently, the crack length actually increases. Now, the stress concentrates on the next bond and breaks it. The process of crack propagation continues, and eventually the material separates at the crack. A crack provides a mechanism by which an external force which is weaker than the bond force can induce a fracture in a material. Note that a crack provides a mechanism by which an external force which is weaker than the bond force can induce a fracture in a material. After crack, the next main reason for the mechanical failure is brittle to ductile transition. So, we have discussed fracture. Now, the second reason, brittle to ductile transition. In some materials, before the fracture occurs, an irreversible elongation occurs. Note the point, an irreversible elongation. At this irreversible elongation, we get a large strain for a small amount of stress. When the stress is removed during this stage, the material will not return to its original length and it will retain certain amount of strain in it. This irreversible elongation process is called the brittle to ductile transition. The irreversible elongation process is called brittle to ductile transition, and this is due to the type of defect called dislocation. The irreversible elongation is due to a defect called dislocation. Now, what are dislocations? Dislocations are regions where a lattice deviation from regular structure extends over a large number of lattice spacings. Once again, dislocations are regions where a lattice deviation from a regular structure extends over a large number of lattice spacings. Look at the figure. The figure illustrates an edge dislocation in a two-dimensional lattice. Atoms in the region of dislocations are weakly bonded to each other. That is a speciality of a dislocation region. Atoms in the region of the dislocations are weakly bonded to each other. In the ductile region of the stress strain curve, one part of the lattice slides over another adjacent part of the lattice. This occurs between sections of the lattice located at the dislocations, not anywhere else. This happens only at the points where the dislocations are seen, and this is because of the weaker bonding force between the atoms. You can increase the stress at which the brittle to ductile transition occur by blocking the movement of these dislocations, and this is done by introducing tiny particles or another material into the lattice, and this method is brilliantly utilized in the making up of steel, where iron carbide particles are precipitated into the steel, which blocks the movement of dislocation. In steel, the dislocations are blocked by introducing iron carbide particles. Now, let us see some of the important mechanical properties of disordered bulk nanostructures. So far, we have discussed about the failure mechanisms of normal grain sized materials, and we are going to the disordered nanostructures, bulk nanostructures, and the properties of them. The first property that we will discuss today is elasticity. A large value of Young's modulus means the material is less elastic. Let us start our discussion by analyzing the relation between a ratio of Young's modulus of steel with nano sized grain to the Young's modulus of steel with conventional sized grain. I will write the two as E and E0. E represents the Young's modulus of steel with nano sized grain, and E0 represents the Young's modulus of steel with conventional sized grain. I take the ratio of the two, E by E0. I draw it on the y axis, and on the x axis I am going to draw, I am going to plot the grain size of the material. So, we have a graph between E by E0 versus the grain size. You can see the plot. In the figure, you can see that E is the elasticity of the steel and E0 is the elasticity of the steel with nano sized grain. From the figure, it is clear that below 20 nanometer, the Young's modulus of the nano sized grain steel decreases from the conventional grain steel. That is, below 20 nanometer, E is less than E0. This means below 20 nanometer grain size, the elasticity of steel increases. When the grain size becomes very less than 5 nanometer, the Young's modulus becomes very small and the steel becomes very much elastic, and this occurs below 5 nanometer. So, you will get a high elastic steel if the size of the nanoparticle of steel decreases or made to decrease below 5 nanometer. One of the main properties that we investigated of a solid is its yield strength. We have discussed elasticity, now we will discuss about yield strength. What is yield strength of a material? Yield strength of a material is the stress at which a material starts to deform plastically. The yield strength of a conventional grain size material is given by Hall-Petch relation. The relation is called Hall-Petch relation, and the relation could be written as sigma y equal to sigma 0 plus k by root d, where sigma 0 is the frictional stress opposing the movement and d is the grain size expressed in micron. D should be expressed in microns and k is a constant. This is a Hall-Petch relation giving the yield strength of a material. Now, there is another property for a solid called hardness. Hardness of the material also follows a similar relation like yield strength. So, we can study both the properties together. Look at the figure. The figure shows a relationship between yield strength and 1 by root d of a iron cobalt alloy. Following the curve, we see that the yield strength of the alloy for a 50 nanometer grain sized material is about 4.1 gigapascal. This shows that the yield strength and hardness of the material increases with decrease in grain size. Once again, the yield strength and hardness both increases with decrease in the grain size. What could be the reason? The reason for this increased yield strength is due to the increase in the grain boundaries with the decrease in grain size. as the grain size decreases, the grain boundaries increases, and this is the reason for the increased yield strength. The deviation from hard pitch behavior is also observed. The deviations are seen for materials with grain size less than 20 nanometer. Deviations are observed for materials with grain size less than 20 nanometer. What we observe is that when the size is less than 20 nanometer, the yield strength becomes independent of grain size. If grain size decreases further, yield strength decreases, which is shown by a negative slope. One more thing which is to be noted is that the conventional deformations due to mobile dislocations are absent in nano-grained materials with grain size less than 30 nanometer. That is, the dislocations are absent in materials with grain size less than 30 nanometer. We shall conclude our discussion on the mechanical properties of disordered bulk nanomaterials after considering another mechanical property, and this property is known as ductility. What is ductility? Ductility is a measure of the capability of the material to withstand a tensile stress. In simpler terms, if a material could be stressed into thin wires, it is said to be ductile. Most nanostructured materials have low ductility and usually they are brittle. So, this is to be noted. Nanostructured materials are usually brittle and they are not ductile. For example, a 30 nanometer grain sized polycrystalline copper, 30 nanometer sized polycrystalline copper has very less elongation, which is less than say 5%, less than 5% elongation, which means they have very small ductility. At the same time, a conventional grain size copper shows an elongation up to 60%. That is, a conventional grain size copper could be stretched to 60% of its original length. Conventional grain sized copper could be stretched to about 60% of its original length. So, they are very ductile. What is the reason? The copper sample of nano-sized grains is a consolidated particulate sample, which possesses two main properties. At first, they possess large residual stress. And they will have a lot of flows. And these two are the reasons for the brittleness of nano-sized grain materials. The residual stress and flows restrict the dislocation movement and makes the material brittle. Now, The question is whether there exists some mechanisms or method by which we could make a ductile bulk nanomaterial. That is, can we make a bulk nanomaterial ductile? Yes, there are methods. One such method is electrodeposition. Electrodeposition. If the nano-grained sample is prepared by electrodeposition, the residual stress approaches 0. Mind you, normally they will have a large residual stress, and if the nanomaterial is made by electrodeposition method, then the residual stress approaches 0 and they will have very few flows, very less flows. Normally they will have a large number of flows in a nanomaterial, but in the case of a nanomaterial, a bulk nanomaterial prepared by electrodeposition, the flows will be very few, and these two are the reasons for the brittleness of a nanostructured bulk material, which we have eliminated now, and we will get a nanomaterial with a large ductility. Look at the figure. The figure shows the stress strain curve of copper prepared by electrodeposition, as we have discussed. We can see that this shows an elongation of more than 30%. In short, the choice of the processing procedure and the effect of the presence of flows has a large effect on the ductility of or brittleness of the material. In this session, we have discussed about the failure mechanisms of conventional grain sized materials such as fracture and brittle to ductile transition. Afterwards, we have seen some important properties of disordered bulk nanostructured materials, and we have discussed the properties elasticity, yield stress, hardness and ductility. In the next session, we will discuss about another category of disordered nano bulk material, and they are called nanostructured multi-layers, and we will discuss about the electrical properties also. Till then,